We've just finished talking about Gauss's law for electricity, and now I'd like to talk about Gauss's law for magnetism. Before that, let me preface this by saying that Gauss's law is a general mathematical result. It's a mathematical theorem, and it applies to any vector field. So there's a Gauss's law for electric field, there's a Gauss's law for magnetic field, there's a Gauss's law for gravitational field, for flow, a field of vectors that represent the flow of a fluid. Um, all of those have a Gauss's law associated with them. And the basic idea behind all of them is that Gauss's law tells us if there's no source or sink inside a surface, I'll explain what that means in just a second, then there's no flux through the surface. Okay, so this is Gauss's law just in general. A source means something that the vectors are pointing away from. It's a source of outward going vectors, and a sink is something that the vectors are pointing towards. So it's like an inward going sink for the vectors. And if there's no source or sink inside a surface, then there can't be any flux, any vector flux through the surface. So let me show you the electricity example first. So if I have a positive charge, we know that the electric field lines point radially away from that electric charge. So a positive charge in an electric field acts like a source. It has vectors that are coming out of it. A negative charge has the same pattern of field lines, but now the lines are going towards it. The vectors are all pointing towards the negative charge, so this is like a sink for the electric field. And for the magnetic field, I'm going to use the bar magnet as my example, as a north and south pole. As we've discussed before, the magnetic field lines emanate from the North Pole, circle around, and enter the South Pole. So in this case, the North Pole would be considered a magnetic field source, and the South Pole would be considered a magnetic field sink. Okay, with that in mind, let me talk about dipoles now. So let's say I have an electric dipole, which is a positive and a negative charge that are close together. And so I have the electric field lines between these. So here's the electric field pattern around an electric dipole. And you can see, as I discussed in the previous video, if I draw a Gaussian surface anywhere in here, so let's say I draw a Gaussian surface right here. Remember, the shape of the Gaussian surface doesn't matter. All that matters is that it's closed, so it is a complete surface with no holes. And my heuristic argument before was that there's no flux through this surface because for every vector that comes in, there's a vector that leaves. For every field line that comes in, there's a field line that's leaving. So the net flux here is 0. Now, what if we take the two ends of the dipole and we separate them? So in the case of an electric dipole, I'm going to move the positive and the negative really far apart, so they're not really interacting with each other. As they can tell, they are alone. Each one is alone. Okay, so I'm going to move them really far apart. Okay, so I've moved them really far apart, so there's a big distance here in between the two, and so they each effectively behave like single charges rather than behaving like a dipole. And here you can see, now if I draw a surface, say around this charge, I'm going to get a net flux. Same down here. If I draw a surface around this charge, I'm going to get a net flux. And that's because the surface contains either a source or a sink. I drew a few extra lines on this side to show you that, notice if I draw a Gaussian surface over here, even though I have a single charge, not a dipole, this Gaussian surface does not contain that charge, and you can see that the flux through this surface is, the net flux is 0. For every field line coming in, there's a field line going out. So again, Gauss's law is consistent. It says that unless our surface contains a source or sink, then the net flux through the surface has to be 0. So here's an example of a surface that has a a source in it, and we have a non-zero net flux. Here's one that has a sink, and we have non-zero net flux. This has no sources or sinks, so it has zero flux. Going back over here, this surface has no sinks in it. If I draw a surface like this, that includes the whole dipole, now the net charge inside is zero, and so the net flux is going to be zero. So the source and the sink cancel each other. Whereas if I draw a Gaussian surface that just encloses the positive end of the dipole, now I have a surface that contains a source and no sinks, just a source, and so I know that the flux of the surface is going to be non-zero. All right, that was for an electric dipole. Now let's look at a magnetic dipole. So the classic example of a magnetic dipole is a bar magnet. And as I just mentioned a minute ago, the magnetic field lines come out of the north and they go into the south. Okay, so as I mentioned before, if I draw a Gaussian surface here outside of the bar magnet, anywhere outside of the bar magnet, I'm going to end up with zero flux to the surface because I have the same number of field lines going in as coming out. And this too is consistent with Gauss's law, which says that since there's no source or sink inside these surfaces, then there should be no flux through the surface. Now, here's the question. Can I, like I did in electric field, in the electric case, can I separate the dipole enough so that I have just a north and just a south? So to do that, I'm going to split the magnet into two magnets. Well, I'm going to split it in half. Let me just start with that. I'm going to split it in half so the north end is up here and the south end is down here. Okay, so now you might think, well, if I draw my Gaussian surface around this, it contains a source of magnetic field only, and therefore there would be a flux through the surface. It turns out, though, nature does not behave that way. If you take a magnet and you split it in the middle, you've created a new south pole right here, and you've created a new north pole right here. So when I draw a circle around this, I have a source and a sink inside of my surface, and so the flux is zero. And same thing down here. Now, you might wonder, what if I have a bar magnet and I draw my surface like this so that it includes only the north pole of the bar magnet? And here, again, there is if you like, there is an unwritten an understood south pole right here and north pole right here. Anywhere that you divide a magnet, whether it's actually splitting it in half or just conceptually splitting it, anywhere you divide it, there's a north and a south end. And in fact, a bar magnet basically consists of a stack of small magnets. And these small magnets consist of a stack of small magnets. And this continues all the way down to the atomic level. Individual atoms have a north and a south magnetic pole. So Gauss's law for a magnetic field basically comes down to the fact that the flux, no matter where I draw my surface, if I'm talking about magnetic field lines, the flux is always zero, because there are no sources or sinks of a magnetic field that can exist by themselves. They have to exist in a source and sink pair. So Gauss's law for magnetism looks exactly like Gauss's law for electricity. I have the flux on the left-hand side, and on the right-hand side is the total enclosed charge. Charge was our source and sink for electricity, but here I've shown that you can't have a source or a sink in magnetism without having one of each. So the flux is always zero in the magnetic case. Right? So this is called Gauss's law for magnetism. So another way of wording all of this is that electricity can have monopoles. What's a monopole? So it's kind of a made-up word, but it basically means if I take a dipole and I split it in half, then you can think of it as I have two monopoles. Okay, so a monopole in electricity is a positive charge or a negative charge. So electricity can have a lone source or a lone sink. So another way of saying that is that electricity can have monopoles. Magnetic field, on the other hand, you cannot have a source or a sink that exists by itself. And so magnetism has no monopoles. And this is effectively another statement of Gauss's law of magnetism. Another way of wording it is that magnetism has no monopoles. Now, could magnetism have monopoles? In theory, yes, and scientists have been looking for them. But none have ever been seen in all the experiments that have been done with magnetism. A magnetic monopole has never been observed. So as far as we know, so far, Gauss's law for magnetism, the right-hand side equals 0, because there are no magnetic monopoles.